Hello, my name is Esther Kim, and we'll be going over Lab 3 of the Black Hole for Physics 2211. So here's our agenda for today. So the goal for part 1 is to find the mass of the black hole using a computational model that simulates the gravitational interaction between a star of a known mass and a black hole. And part 2 is using a similar computational model. We find the initial velocity needed for a spaceship to fly close to the black hole before escaping the black hole before hitting the planet. And the findings we have here are what we will be finding today. So the first key concept is Newton's second law, which states that the new force of an object is the change in momentum over the change in time, which could be manipulated and rewritten into the velocity update formula, which could also be rewritten into the position update formula, as shown to the right. Another key concept is the parallel and perpendicular components of the net force. A net force has components that are related to the direction of motion. The positive p has p hat axis points in the direction of motion, and it is related to the change in speed of an object. The perpendicular component, which is n hat, is obviously perpendicular to the parallel component, and the positive n hat axis points to the center of the turning circle. It is related to the change in direction of an object. And the F net forces of both the parallel and perpendicular are shown to the left. Another concept we have to understand is the gravitational force, the universal law of gravitation. We wrote the formula is written down below, where an object due to another object is an attractive force that is defined. And according to Newton's third law, because they're attracted to each other, the negative side indicates the attractive force, which is shown below. So the free body diagrams here are different for both part 1 and part 2. For part 1, it's the attractive forces of the black hole and the star. And so we will be looking for the mass of the black hole for this one. The system is the star, and the surroundings is the black hole in the space. Part 2, similar occasion where they are both attracted to each other, except that we'll be focused on velocity and the spaceship. So the system is the star and the planet, and the surrounding is the black hole in space. And in order for you to find part 1, you will need to have, oh, sorry, not part 1. For you to have part 2 of the velocity, you will need to have both masses of the black hole and the star. So here's the computational model for part 1. There have been some changes made. These changes were made based off the key concepts that we knew and the formulas that we knew. And so we basically just manipulated it into code. So such as like delta V, delta P, these are like change in velocity and change in position. We basically use those formulas, which you can see in lines 160 and 169. And that is just one example. We basically just manipulated our key concepts, sorry, our code into matching it to our key concepts. And on the right, you see the image of basically how the arrows should be pointing in part 1. In part 2, we did the similar thing where we took the key concept and the formulas that we knew and we manipulated it into code so that we can create this computational model. And onto the right, you can see what it's basically supposed to look like. So for part 1, the results are shown in the first 4 lines. The result of the mass of the black hole is basically determined based off all the averages of the mass values, and so the final result was 2.44 times 10 to the 34th kilograms. And the star follows an elliptical orbit around the black hole due to the net force. In this elliptical orbit, the gravitational force is smaller in magnitude when the star is farther away from the black hole compared to when the star is close to the black hole. A possible error, which will both apply in part 1 and part 2, is the rounding values, because we are taking the average. And so if we don't round correctly, we could undershoot it or overshoot it, depending on how you round. So in part 2, the first 3 are basically the results that we get. The shortest distance between the spaceship and the black hole is 2.41 times 10 to the 8 meters. The initial velocity indicates that the spaceship is moving to the left and up, and the spaceship experiences a maximum gravitational force from the black hole at its shortest distance to the black hole. The ship is shot out to the black hole planet system due to the gravitational force experienced by the black hole. And like I mentioned earlier, possible sources of error is rounding values of the black hole, because we could be overshooting it or undershooting it. So what does this mean? The net force is equivalent to the rate of change in momentum when the net force and its parallel and perpendicular components differ from the rate of change of momentum and its parallel and perpendicular components. The parallel and perpendicular components of the net force are equivalent to the rate of change of momentum. Now, what if the initial velocity of your spaceship needs to have to enter some kind of orbit into the black hole? So compared to the initial velocity in part 2, the velocity to create the orbit should have a lesser magnitude in the x component and a greater magnitude in the y component, and this will lead to an initial trajectory that is more vertical. And with this velocity, the spaceship orbits around the black hole with the trajectory shown to the left without hitting the planet. Thank you.